Good morning, students. Today our session starts with continuation of the magnetism of matter. Let us start our discussion with another definition, pole strength. Pole strength. First, let me give the definition of the pole strength. Pole strength means it is the strength or ability of the magnetic pole to attract or repel another magnetic pole. So, it is the strength or ability of the pole to attract or repel another magnetic pole. So, this is nothing but pole strength. Strength or ability of the pole to attract or repel another magnetic pole is nothing but pole strength. Generally, pole strength, it is denoted by small m, and it is vector, generally it is a scalar quantity, and its unit ampere meter, and its a dimensional formula only AL or IL. And if you write the full form of the dimensional formula, this is m power 0, L power 1, T power 0, I power 1 or A power 1. Suppose if you take a bar magnet, in the yesterday class clearly I explained about the bar magnet. It is commonly used form of artificial magnet. This is a bar magnet with the south and the north poles. Generally, the magnetic moment for the south pole is the negative and the north pole is the positive. Keep those lines in mind. I said definition of the pole strength. Pole strength denoted by the symbol small m, and it is the scalar quantity. Its unit ampere meter. I given dimensional formula. After that I said pole strength m is negative for south pole and pole strength m is positive for north pole. So, that is the pole strength. And after that, let us see the dependence and independence of the pole strength. Generally, pole strength depends upon number one, nature of material, and number two, area of cross section, or it is said to be the face area of the magnet, and third one, a state or level of magnetization, simply magnetism. So, these are the dependence. Let us see the independence of the pole strength. Pole strength independent on shape of the poles, or shape of the magnet. Right. So, today our session started with another new definition of the pole strength. Pole strength is nothing but is an ability, is a strength or power of the pole to attract or repel another magnetic pole is nothing but pole strength. Basically, pole strength denoted by the symbol small m is the scalar quantity, and also unit of the pole strength ampere meter. I given the dimensional formula. Generally, pole strength is the positive for the north pole, negative for the south pole as shown in the figure. Keep those lines in mind. So, that about the pole strength. And here I would like to give one note point which is very, very important for objective. Suppose assume it is the bar magnet. It's a bar magnet. See, this is the south pole and it is the north pole. Just I said magnetic pole strength negative for the south pole, positive for north pole. And here the face area or area of cross section of the magnet is A. Generally, pole strength is directly proportional to area or face area or area of cross section, which is directly proportional to the flux. It will come later, just keep in the mind. Pole strength is directly proportional to area, proportional to the magnetic flux. For example, if area made by halved, area of cross section is halved, then automatically the pole strength become halved and flux is also halved. Similarly, if the area of cross section or face area made n times, that is decreased by the n times as shown in the figure, therefore, it is also m by n, it is also pi by n, like that. Keep those lines in mind. And see some examples. The first example, this is one bar magnet. This is the south pole and it is the north pole. Here it is made two pieces as shown in the figure. It is made two pieces as shown in the figure. If you have been observed the diagram, this is the face area or area of cross section. Even if you cut magnet as shown in the figure, it is made into the two pieces as shown in the figure, first piece, second piece. For both pieces, there is no change in area of cross section. Face area is not changing. If face area is not changing, actually what is the relation? Pole strength is directly proportional to the face area. If the face area is not changing, then what is the new pole strength of the each piece? That is m only. Our answer, pole strength of this piece, actually pole strength of this one is the minus m and plus m. So, in a bar magnet, both poles having the same strength, that is same pole strength, of course signs are different. Even though if you cut the magnet as shown in the figure, face area is not changing, face area is not changing, obviously pole strength is not changing. Therefore, pole strength of this piece is same m, pole strength of this piece is also same m. And let us move to one more example. This is an example 2. Assume it is a bar magnet. And these are the two poles of the bar magnet, south pole and north pole. Now, it is made two pieces as shown in the figure. So, initially what is the face area here? Face area or area of cross section is A. It is made into the two pieces. This is the first piece and it is the second piece. Area of cross section here A by 2, here A by 2. Here area of cross section changing. Area of cross section changing mean pole strength also changing. Therefore, what is the relation actually? Pole strength is directly proportional to the face area. Here it is made half. Obviously, pole strength is also half. Therefore, the new pole strength of the each piece m dash is equal to, let us write m by 2. So, these type of problems important for objective examination, that is for JEE main. And let me give one more example, example 3. In this example 3, see this is the bar magnet with the south and the north poles. Now it is made n equal pieces as shown in the figure, n equal pieces. Area of cross section, initially area of cross section is A. If it is made n equal pieces, all the pieces will have the same face area, same area of cross section. Therefore, area of cross section is not changing, m proportional to A. Therefore, m dash is equal to m only. Pole strength is not changed. Pole strength is same for all the pieces. Otherwise, here I will write example 4. Assume it is a bar magnet. So, south pole and it is the north pole. Now, area of cross section is A. Pole strength for this one minus m, for this m plus m. So, once again I am telling, in a bar magnet there exists a pair of opposite poles, those two poles having same strength, that is same pole strength, but signs are different. Now, it is made n equal pieces as shown in the figure, n equal pieces as shown in the figure, n equal pieces as shown in the figure. How it is made n equal pieces? Along the lengthwise. So, what happened? Area of cross section changes. Area of cross section changes. Basically, what is the relation? Pole strength is directly proportional to area of cross section. Now, it become A by n because it is made n pieces. So, that what about the pole strength? This is m by n. Keep those lines in mind. Therefore, new pole strength of the each piece is equal to m by n. Like that, pole strength may vary. Okay, students. So, pole strength concept, listen carefully and note it down carefully. All points regarding to the pole strength I have explained, and a note point also I said. After that, I given the 4 examples. They covered different models. This is the pole strength. So, pole strength dependence and independence also I have explained. Pole strength depends upon mainly these 3 points. Pole strength depends upon nature of the material and also area of cross section. Area of cross section means face area. Third one is state or level of magnetism. And finally, pole strength independent on shape of the poles or shape of the magnet. Keep those lines in mind. Then after, let us move to another definition, magnetic length. Another definition, magnetic length. Right. We are very familiar about the bar magnet. Suppose if you have been observed the bar magnet, this is the bar magnet. In the last class, clearly I have explained about the magnetic poles. When a bar magnet dipped into the iron fillings or iron dust, more number of iron fillings are cling at the ends rather than at center. That it represents the power or the attraction power is more at the ends rather than central. That center is said to be neutral region. Attraction is a minimum at the center. That and all we discussed in the last class. And moreover, the magnetic poles, for example, see this is the bar magnet. The magnetic poles are not located exactly at end points. Clear to one another? The magnetic poles, south pole and north pole, not located exactly at the ends, but they may located a little bit distance away from the end, in front of the end of the magnet. Right? I hope you understood. This is the position of the south pole, this is the position of the north pole, but not this is the position of the north pole. This is the position of the south pole. Understood what I said? So, the position of the pole is not exactly at end point of the magnet, it is just in front of the end of the magnet like this. It is not position of the south pole, it is not position of the north pole. This is the position of the south pole, it is the position of the north pole. So, the poles are located just in front of the or just away from the end of the magnet. So, if you have been observed the diagram, this is the position of the south pole and it is the position of the north pole. The distance between or simply the shortest distance between poles of the magnet is said to be the magnetic length. This magnetic length is denoted by 2L, right. 2L mean where to where you have to take the length. Position of the south pole to the position of the north pole, the shortest distance between the poles of the magnet is said to be the magnetic length, and often we call with different names, magnetic length, or it is actual length, or it is also said to be effective length. We call with different names, magnetic length or actual length or effective length. Right. First, let me write the definition of the magnetic length. The shortest length between or distance between the shortest length or distance between, let me write distance, the shortest distance between poles of the magnet is called magnetic length. Through diagram we will show it. This is the bar magnet. Assume it is the position of the south pole, it is the position of the north pole. Now, this is the shortest distance between the poles of the magnet, therefore, it is denoted by 2L. Of course, it is a vector quantity. So, here the magnetic length, it is denoted by 2L. It is a vector quantity. The unit of the magnetic length we can represent either in meter or centimeter. And a dimensional formula, you know dimensional formula for length, only L, or the full form m power 0 L t power 0, that is a dimensional formula. Of course, it is a vector quantity, we have to represent the direction also. Direction is always from south to north pole. Direction of the magnetic length is always from south to north pole. Keep those lines in mind. Clear. Then after, this is the magnetic length. Let us see what about the geometric length. So, geometric length means the total length of the magnet is said to be geometric length. First, let me write the definition. The total length of the magnet is called geometric length. Suppose let me represent the geometric length through the diagram. This is the position of the south pole, this is the position of the north pole, and see the shortest distance between the poles of the magnet is said to be the magnetic length, denoted with the 2L. But the total length of the magnet, this is the total length of the magnet, total length of the magnet, suppose it is the A and it is the B. The total length of the magnet is said to be geometric length, this is said to be magnetic length, this is the magnetic length. Of course, it is 2L, we know that, 2L. See, what is the definition of the magnetic length? The total length of the magnet is said to be the magnetic length, that is AB is the magnetic length and SN is the geometric length. Let me write AB is geometric length. Here SN bar, why I have written SN bar? Because magnetic length is the vector quantity whereas the geometric length is a scalar quantity. So, SN bar is equal to magnetic length, keep carefully. So, magnetic length. Now, the relation between magnetic length and geometric length. So, relation between the magnetic length and geometric length, magnetic length is equal to, it is the 5/6 times of geometric length. Here which represent the magnetic length? Magnetic length represented by SN or SN bar is equal to 5/6 times of geometric length is the AB. Now, magnetic length SN bar is equal to 5/6, that is nothing but 84% in terms of percentage, 84% of geometric length. And you have been observed the magnetic length is always less than geometric length. Magnetic length is always less than geometric length. So, this is about magnetic length and geometric length. Now, let us see the dependence and independence of the magnetic length. Magnetic length depends on number 1, position of the poles, or shape of magnet, or shape of magnetic poles. Second one, bending of magnet, Third one is Y cutting. Y cutting means the magnet is cutted along the Y direction, that is a Y cutting. Otherwise, magnet is cutted along the X direction mean X cutting. This is the dependence of the magnetic length. Another one, magnetic length independent on number 1, nature of material, number 2, magnetic length independent on nature of the material, and also state or level of magnetism, state or level of magnetism. Third one, X cutting. I will explain these through problems. Meanwhile, just note it down. So, magnetic length depends on, see carefully, magnetic length depends on, dependence I am telling. One is position of the poles or position of the magnet or shape of the magnet. Second one is bending of the magnet. Third one is Y cutting. Y cutting means the magnet is cutted along the Y direction. Second one, magnetic length independent on. This is the independence of magnetic length. Number one, nature of the material. Number two, state or level of magnetism. Third one is X cutting. X cutting. And finally, I will give one note point. This is the key point. Here the magnetic length depends on position of poles but not shape. Right? Magnetic length depends on position of the poles but not shape. Second one, magnetic length always less than geometric length, just now I said. So, these are the magnetic length and geometric length, relation between the magnetic length and geometric length, dependence and independence of the magnetic length. Then after, I will move to some JE applications. JE applications. First application, suppose it is the bar magnet. Bar magnet. This is the position of the south pole and it is the position of the north pole. Now, just I explain, the poles of the magnet are not exactly located at ends, they are just away from the end. Suppose the distance from end of the magnet to the position of the pole is say some x. This is also position of the pole to end of the magnet is x, whereas obviously we know the distance between or the shortest distance between poles of the magnet is nothing but magnetic length. Now, the total length of the magnet is said to be geometric length. Now, in this application we are going to find the x value. X is equal to how much? That means find the position of the pole from the end of the magnet. That is the question. Find the position of the pole from end of the magnet. So, actually if you have been observed the diagram from geometry, here the geometric length that must be equal to sum of x plus magnetic length plus x. Therefore, geometric length is equal to x plus x, that it become 2x plus magnetic length. Now, geometric length or directly take 2x. 2x is equal to geometric length minus magnetic length, or x is equal to geometric length minus magnetic length by 2. This is the shortcut formula to find the position of the pole from end of the magnet. Position of the pole from end of the magnet. These type of applications important to solve the questions either in the JEE Main or JEE Advanced. And let me solve one problem based on this. Okay, first I finish the application 2 also, then we move to problems. Application 2. In the application 2, this is the bar magnet. This is the south pole and north pole. Actually, this is the total length of the magnet, they given L. This is the magnetic length 2L. So, after seeing the diagram directly we can give answer. Magnetic length is equal to shortest distance between the poles of the magnet, that is equal to 2L. Geometric length is equal to, so total length of the magnet is equal to L. So, that is fine. It is a simple question. B. See this one. Now, if a bar magnet which is bent in the form of a arc of the circle as shown in the figure. The bar magnet is bent in the form of an arc of the circle. This is the south pole, whereas it is the north pole. Now, this is the R radius. Actually, if you consider the full circle, radius R. Right. Now, in this question, they are asking what is the magnetic length first of all? ML, magnetic length. Magnetic length is nothing but shortest distance between the poles of the magnet. So, what about the shortest distance between the poles of the magnet? R plus R, 2R. And whereas the geometric length is nothing but total length of the magnet. That is, total length of the magnet is nothing but this length we want. That is the half of the circumference of the circle, that is nothing but pi r. Now, let us move to problems, the basic problems. First problem. Find the magnetic length if geometric length is 12 centimeter. This is the first question. Find the magnetic length if geometric length is 12 centimeter. We know the relation between magnetic length and geometric length. So, that is, you know, Sn bar is equal to 5 by 6 times of geometric length AB. Sn bar is equal to 5 by 6 times of AB. Sn bar is nothing but a magnetic length. Magnetic length is equal to 5 by 6 times of geometric length. But they given geometric length is equal to 12 centimeter. So, substitute here. Magnetic length is equal to 5 by 6 into 12. So, 6 1 6 2s, 5 into 2, 10 centimeter. Therefore, magnetic length is equal to 10 centimeter. That is the first problem. Let us move to second problem. Question is, find the geometric length if magnetic length is 15 centimeter. Got the question? Find the geometric length if the magnetic length is 15 centimeter. How we solve the question? First, take the relation between the magnetic length and geometric length. What is the relation between the magnetic length and geometric length? Magnetic length is equal to, directly I am writing, 5 by 6 times of geometric length, that is AB. They given the magnetic length as 15 centimeter. Therefore, 15 is equal to 5 by 6 into AB. AB is nothing but, directly I am writing, geometric length. So, 5 ones, 5 threes, 3 into 6, 18. Therefore, geometric length is equal to 18 centimeter. Now, third problem. Here I will write the third problem. Third problem. Question is, find the position of north pole from end of the magnet. That is a given question. So, find the position of north pole from end of the magnet if magnetic length is 20 centimeter. The given magnetic length is 20 centimeter. Now, if you have been observed the diagram, this is the bar magnet. This is the north pole and it is the south pole. Now, the distance from south pole, here I will write south pole, this is the north pole. The distance from north pole to end of the magnet is x. Similarly, south pole to end of the magnet is also x. So, they are asking the x value, but actually they given the magnetic length. Magnetic length is equal to, they said 20 centimeter. That is the given data. But you see what is the formula for x? I said shortcut formula, x equal to geometric length, see this one, minus magnetic length by 2. This formula we have to use. But there you know only the magnetic length, but you don't know geometric length. Find the geometric length by using the relation. Geometric length is equal to, or take directly formula, magnetic length is equal to 5 by 6 times of geometric length. Magnetic length they given 20, 20 is equal to 5 by 6 into geometric length. 5 ones 5 fours, 4 into 6 24. Therefore, geometric length is equal to 24 centimeter. Substitute here, x is equal to 24 minus 20 by 2, that is equal to 4 by 2, that is the 2. So, x is equal to 2 centimeter. This is the position of the north pole from end of the magnet. Like that we can solve the questions which are important for JEE Main as well as the JEE Advanced. So, this is the topic regarding magnetic length and geometric length. And let us move to another important definition, magnetic moment. Magnetic moment. Actually, what is a bar magnet? The bar magnet is commonly used in the form of artificial magnet. Suppose if you take a bar magnet, this is the bar magnet. See, this is the south pole and it is the north pole. Of course, it is the center of the magnet. This is the center. The line which is passing through the center and parallel to length of the magnet. The line which is passing through the center and parallel to length of the magnet, it is said to be axial line. Axial line. Now, see, this is the center. The line which is passing through center and it is perpendicular to axial line, it is said to be equatorial line. Equatorial line. Equatorial line. So, the line which is passing through center parallel to the length is said to be axial line. The line which is passing through center perpendicular to the axial line is said to be the equatorial line. And after that, what is the magnetic dipole? Magnetic dipole. These are the basic definitions which help you a lot to understand the questions from JEE Main and JEE Advanced. Magnetic dipole. Actually, di mean two, poles mean magnetic poles. Where the two magnetic poles exist, obviously in bar magnet or in the case of magnetic needle. Therefore, magnetic dipole mean this is the configuration in which, of course, bar magnet, the configuration in which two equal opposite poles having the same strength available, that configuration is said to be, that system is said to be the magnetic dipole, where the equal opposite poles are exist. Suppose it is the south pole and it is the north pole. The two poles having the same strength, two poles having the same strength. Also they are the opposite poles, because its pole strength is the negative, its pole strength is the positive. Therefore, the configuration in which two equal opposite poles separated by certain distance. So what is the distance between the two poles? Obviously we know 2L, that is a magnetic length. The configuration in which the system possesses two equal opposite poles separated by certain distance, that is said to be the magnetic dipole. So examples of the magnetic dipole: bar magnet, and also magnetic needle. Magnetic needle is said to be the compass. Magnetic needle is said to be compass. So that is the magnetic dipole and a bar magnet, equatorial line and axial line. So what is the magnetic moment? See, this is the bar magnet. First let me give the definition. The product of pole strength and its magnetic length is called magnetic moment. Suppose take this is the bar magnet. Is a south pole and it is a north pole. Pole strength of the magnet is M. Magnetic length is the 2L. This is the magnetic length. From definition, the product of pole strength and a magnetic length is nothing but a magnetic moment. So M into 2L is nothing but a magnetic moment. Suppose if you take the vector form, this is nothing but M bar. M bar is equal to 2L bar into M, is not cross product, just only into M, because the multiplication of the scalar with the vector. This is the vector form. And let us see the unit and the dimension and the direction. Unit is ampere meter square or joule per Tesla, different units are there, or it is the Newton meter cube per Weber. And the dimensional formula IL square, the full form m power 0 L square T power 0 I power 1. Direction also important. Direction of the magnetic moment is